Hello, everyone. Today is the final lesson on momentum and impulse, and this will simply be this one page and a bit, so a very quick lesson indeed. So, momentum and impulse, we have discussed a bit about this already, but we're just going to go through these notes here and see if we have any extra thoughts. So, to safely stop a moving vehicle, its braking system applies an impulse by exerting a force, right? And remember that an impulse is equal to a force times a time on the wheels for a long period of time. So typically when you start to brake, compared to a crash or compared to an uncomfortable moment in the car, typically if you want to brake well while driving, you'll apply the force apply the impulse over a long period of time. So this force of the brakes will be applied over a long period of time, and the total impulse will be actually sort of this force spread over time, and the amount of force that has to be used is actually going to be pretty minimal. So thinking about this equation, we can kind of imagine that if time is very big, then force can be small, and we will still get the impulse we need to stop the car. And meanwhile, the passengers on the inside of the car will be experiencing a small amount of force, and that small amount of force will make it quite a comfortable experience. Think about also an airplane landing. If you've ever been on an airplane, the difference between a good landing and a bad landing is how smooth, and by smooth, they typically mean how long the landing process takes. If the landing time is long and the plane slowly and gently touches down on the ground and then it starts applying its brakes, then the amount of force the individuals on the inside of the plane are feeling is small. If the plane is making a hard landing, then we're going to be expecting that the time is going to be small and the force will be large. And so for the passengers on the inside of the plane, they will also be feeling this force because there'll be equal and opposite forces everywhere all over the plane. And those forces on the individuals will be uncomfortable, and that's where you'll be feeling jostled around inside the car, or inside the airplane. So, in a collision, the same impulse is applied over a very short duration of time. So think about it as the impulse is whatever is the thing required to stop this vehicle from moving. And if we think of these impulses, the energy necessary to stop a vehicle, these impulses will be the same, but the time that the impulses occur over is different. In a collision, the time is very short. In a braking scenario, a comfortable braking scenario, the time is long. So the difference of the force applying to the car and applying to the occupants inside is going to be different. It's sort of they're proportional. They're inversely proportional. So if the time is short, the force is large. If the time is long, the force is low. So in order to cushion the blow, manufacturers have invented several devices that use impulse-momentum relationships to decrease the force applied on cars. This lesson will introduce you to several of these devices. So in the last lesson, you learned that momentum is a product of mass and velocity. So let's put that in as well. Mass times velocity. Therefore, if either your mass or your velocity increases, so does momentum. You also learned that the impulse is a vector quantity and is a product of force and time. So we apply a force over a period of time to change the momentum of an object, and this is the impulse. A good illustration of this concept is the egg toss. If you toss an egg on the concrete, it will crack open upon impact with the ground. So you toss an egg, then it will crack open upon the impact of the ground. That's because a large force has been applied to split in over a split second, which has stopped the momentum of the egg. A large force, so we're talking about the large force applied over a small time to give us that impulse required to stop the egg. The egg did stop, but the force was so large that it overcomes the the forces that hold the whole egg together, and the egg loses its construction. It cracks open. The egg shell can't handle this much force. You could also bring the egg's momentum to 0 by throwing the egg into a cushion or into a mattress. This time, the impulse is the same. You were talking about an impulse to take its momentum to 0, but it is spread out over a longer period of time so that the force is much less. So if we think about that egg, the egg landing on the concrete, you've just got a egg hitting the concrete. So the time and the distance traveled is going to be a very small time. I don't know what I'm drawing here. Let me just think about this. So this is going to be the case where we have the egg does stop moving, so the impulse is effective, but the force is high because the time is small. If the egg hits a pillow, my pillow here, then the egg will travel through the pillow and land on the bottom of the pillow, and it will have this whole time here, right? This will be time. So in this case, the impulse will be equal to a smaller force because the time is larger. The impulses are the same, so these are the same because this is simply the value. This is the same impulse. Reducing momentum to 0, but the time is different. Different times. Different time. And so this is this can be a little bit of a tricky concept. This is because we don't really think about the time component when we are thinking. This is my fringe on my pillow here. I don't know if that's actually helping my pillow situation. Maybe I'll draw a different kind of pillow. I got it. I want to do one of these pillows. Okay. Sure, that's kind of a pillow. Okay. So we also discussed the idea of the second collision. So the first and second collision in a car crash. So for example, a car colliding with a building, the first collision is upon the impact and involves only the car and the building. At this point, the car's momentum has been reduced to 0, and the force was very great. So the car hits you got your car, and it hits the wall, right? And of this building, this is an instantaneous thing. So we are talking about a very high impulse where the force is very high and the time is very small. And that's the impulse required to reduce this mass down to a 0 momentum. Remember that the passenger of the car will continue to move. So there's still a person inside, right? And they are going to continue to move. Now that person must also experience the same impulse or a similar impulse because their mass has to stop moving, or it will stop moving. So this person on the inside has to have their own impulse. And the trick is, are they going to hit a hard steering wheel and their momentum is going to stop instantaneously, or are they going to hit something soft like a seatbelt or even an airbag? So airbags and seatbelts essentially increase the value of T by keeping the body in contact with something for a longer period of time. Notice that your seatbelt, when you feel it in the car, it is not tight to your body. It actually has give. It's supposed to have give. If the seatbelt was tight and it held in position and did not move, then that would actually be a problem because that would mean that your time to slowing down to 0 velocity would be short. If the seatbelt has some give to it, then you'll stay in contact with the seatbelt as it starts to put force on you to slow you down, but you'll stay in contact with it for a longer period of time as it slowly tightens up. Slowly in this case, in still milliseconds or maybe seconds, but it's better than the instantaneous collision. So in this way, the force becomes smaller on the person because the time is dilated, or its time is slowed, is increased. Time is increased by the seatbelt, by the airbag. Airbag does the same thing. Airbags, lots of cars have multiple airbags now. When you're hitting that airbag, the airbag is not supposed to stay inflated. The airbag is there to slowly deflate, and so that it's actually, I think it impacts you immediately with a force of the airbag hitting you, and then it deflates as you fall into it. And that deflation is going to increase the amount of time that your body is slowing down. And by increasing the amount of time that your body is slowing down, it decreases the force by putting that force over a longer period of time. So the second collision occurs when the passenger of the car hit the steering wheel or other objects that will reduce the momentum to zero. There are many devices that are now used to help lessen the damage caused by second collisions, such as airbags and seatbelts. And I will try to post some videos about the airbags and seatbelts and the forces that are effective from those. Seatbelts, airbags, bumpers, head restraints, crumple zones on cars, child safety seats, and rollover protective structures all work as a team of cushioning devices to keep you as safe as possible in a vehicle. Now that you know more about what a collision does to a physical structure of a car, you'll go on to learn what happens to the energy in a car when it comes to a sudden and forceful stop. In the next learning experience, you will be introduced to the law of conservation of energy and the different types of energy. You will be also determine how the law is related to the car collisions while identifying the conversions of energy in a car collision. So that's where we're going next, is to talk about energy. I will post an assignment for tomorrow that will sort of finalize any of these calculation sections on the various momentum and speed and acceleration calculations. It'll be a little bit of a bigger assignment, and that will cover the majority of this booklet, and then we'll have one final assignment at the end about the conservation of energy. But other than that, hope you have a great day, and we'll talk to you soon.